Okay, welcome everybody. So today we're going to be talking about logic block architecture. And let's see if I can find my pen. There it is. Okay, so let's see if this will advance. So assignment 2 is due next Tuesday, November 3rd. So if there are any questions, you ask me any ones that are not too long right now. You can also post on Piazza, or you can email me or post on Piazza if you'd like a Zoom meeting. There are some good questions on Piazza, so if you haven't been watching them, some have been private, but some have been public as well that you can see. So there's a good question about exactly what's the definition of operations when you're computing gigaops per second for efficiency comparisons across platforms. So basically there's 17 operations, 9 multiplies, 8 additions to compute a single filter times a certain window and produce a single output pixel. So that's true even if you come up with clever tricks where you're able to reduce some of those operations in some way. When we're comparing platforms, we don't want to take away the value of those tricks. So you're going to count it as you've computed 17 things, even if you found a clever way to get rid of some of them. On Quarkus, there's an updated test bench. You don't need to get this updated test bench if you haven't had any issues, but at least one student had an issue where the RTL simulation did not match. Actually, I have a mistake here on the slide. So where I've put RTL simulation, that's really gate level simulation. We didn't hold the reset high for very long, just for one cycle in the test bench. And when you go to gate level simulation, you have delays. At least one student found that meant that the design didn't reset properly. So we've changed the test bench to hold reset high for longer to make sure that you don't have any issues with that. If you haven't had any issues, you don't have to worry about it. If you do, you can try this new test bench. On 4 p.m. on Friday, I'll go on Zoom and have a coffee. So if you have any questions about the course or anything you want to chat about, feel free to join it. So let me pause for a second, see if there are anybody has any questions about assignment 2. If not, I'll move on. So any questions from anybody? Okay. In that case, I'll keep going.
There is one question in the chat menu.
Oh, I see it. For A2, does a circuit need to have registered output? Yeah, you should register your outputs. It's good practice. It ensures that your timing analysis is correct and that you're being nice to whatever receives your outputs because you're cleaning up the signal as much as possible. Given the computation you're doing, I think it'd be hard not to have registers around your outputs, but best practice would be to register them right when they go out. Does that answer your question? Yeah, and Gil has a good point. Like if you actually manage to remove, if you actually wind up with only input registers and no other registers anywhere, then Quartus will not properly timing analyze your design. It will basically go, this runs incredibly fast because there are no paths between registers. So we definitely don't want to get that. If you find your designs running unbelievably fast, even though you haven't like a gigahertz or so, even though you haven't optimized it that much, that usually indicates you don't have any output registers. Question on the marks for the previous readings. Will we get marks for them? Yeah, you will. Sorry, Andrew and I are a bit behind on that. And I know Andrew's focusing on getting the lab 1 marks back before you have lab 2. Andrew, how was that looking? It's a good question.
Not super good. I sent you an update email regarding that.
Okay, so I guess we'll talk offline. Maybe I can help. Yeah. We can parallelize it. Is that a feasible solution?
Probably.
Okay.
We can discuss it after the lecture.
Yes, the answer is you will. Sorry that it's taking us a while. Okay, prior background readings. So we're going to cover a couple of things today, and depending on how time goes, possibly part of your next week's reading too. So starting at the bottom here, 2 weeks ago, you had a classic paper on logic block architecture assigned that we're going to talk about in detail in this class, because it looks at a lot of the key trends in logic block design. And then the second half of today, we're going to talk about another key paper by David Lewis and his colleagues at Altera on Stratix 2. And this really changed the way lookup tables are designed and became dominant. So both these papers kind of reflect major changes in the way people design FPGA logic, which is the reason we're looking at those. Okay, reading for next week, another industrial paper. So David Liu is also of Altera, is also the first author on this one. So some further enhancements that happened in Stratix 5. And this was a major change in essentially how the registers are implemented in FPGAs. Okay, so let's move on to logic block architecture. So last week, we kind of went through a simple FPGA and we looked at how the circuitry was built. We estimated its area by hand so that we could see most of the area was in the routing and get a feel for how area estimators work for FPGAs. What we're going to do today is we're just going to review some published results that use more complicated flows, but they're basically automating a lot of what we did by hand with more accurate models. So the kind of logic blocks that we're going to look at first, and the kind of logic block that's really dominant now, is called a logic cluster sometimes. And what it is it's a two-level hierarchy. So this is, again, something we talked about 2 weeks ago, that island-style FPGAs have adopted this idea of having a little bit of hierarchy in their lowest level blocks. So we have what's called a basic logic element by Ahmed and Rose. In this case, a 4-input lookup table and a D flip-flop, and you can pick either of the outputs. So kind of a classic FPGA logic element. And you take that and you build a logic cluster out of it. So essentially a small, very small hierarchical FPGA. You take several of those basic logic elements and you put them all in one logic block. And the standard notation for that is to call that number n. How many of these basic logic elements do we put inside of a logic cluster? Standard notation for how big the lookup table is k for the number of inputs. Again, we talked about this a couple of weeks ago. The key parameter of these logic clusters is, so one is how many BLEs you put in them, n. Okay. Another is how many inputs you bring in from the outside world, I. Now if we ignore the clock, we would never need more inputs than k times n, because we have n BLEs. Each of them has a lookup table with k inputs. So there's no purpose in bringing in more than kn inputs, given that we're bringing the clock in on its own input. But in general, we know that circuits have locality, so we're probably going to wind up reusing some of these inputs multiple times. They'll feed different lookup tables. So we have this local routing that can basically broadcast these I inputs, choose which one of these I inputs gets sent to which input on these various BLEs or lookup tables. And because of that, because we expect some of these lookup tables may use the same signal, we don't need to bring in k times n different inputs. And that makes our local routing cheaper. And it also reduces the number of multiplexers we need out here connecting to the general routing, which makes that cheaper. So making I smaller is good, as long as it doesn't make it really hard for us to actually use all of these logic blocks. The other way that we can reduce our number of inputs that we bring into the logic cluster is we can basically reuse things that we already generated in the logic cluster. So we have every one of these BLEs produces one output in the architecture I've just shown you. So we have n of these signals generated inside the cluster, and we can feed them back into this local routing. And that, again, reduces demand for signals from the outside world. Lets us get by with a smaller number of inputs, which is going to save us routing ports and save us area. So we use this local routing for two things: to send our outputs back to the BLE inputs, and to distribute this smaller number I of cluster inputs to the lookup table inputs. And in the architectures we're going to look at, there's just one clock that fans out to all the registers, because usually you don't need that much flexibility on clocking. Okay, so some architecture questions. First, what's the best logic element? So they're mostly lookup table based. And we talked about this a couple weeks ago. So this is like a test of who remembers. Like, why are lookup tables dominant? What's good about them? So just type it in the chat or unmute yourself if you got an idea. Yeah, so they can implement any, as Edwin said, they can implement any K input function. So that's good. And that's really, I guess, that's really kind of the key to both of their advantages. They're an efficient synthesis target because it's easy to tell if something fits in a lookup table. If it has K or fewer inputs, it fits. So that's nice for your CAD tools. And because they can implement any function of K inputs, you get a lot of functionality for not that many routing ports. And we already saw this last week that routing ports are very expensive. They're typically a 20-to-1 mux or greater. This is part of how you design your FPGA routing architecture, but these would be typical numbers. So that's fairly expensive. We saw last week that actually a single routing port can cost more, about the same or even more than your entire lookup table if your lookup table only has 4 inputs. So routing ports are really expensive. A lookup table gets a lot of functionality for every single routing port because it can do any function of its inputs. So you really can't do any better than that if you're trying to minimize routing ports. Okay, so that doesn't answer the question of what's the best LUT size. So we've got a trade-off there. Basically, a larger LUT is going to be able to capture more logic, so that's good. But we already know that its area grows exponentially with K, so that's not very good. So it's not obvious what the best lookup table size is. And that's one of the things that Ahmed and Rose set out to answer. Okay, so other questions. Should we combine lookup tables into a logic cluster? So I already talked about this. That forms this 2-level hierarchy. It helps your CAD tools. It allows some word-wide signals like clock and clock enable and so on that don't need as much flexibility. We can kind of just share those across the whole logic cluster. So logic cluster gives us a natural way to do that. So we talked about that a couple of weeks ago. Lots of good reasons to do this. But we need to quantify. Seems like it could be a good idea. Is it really a good idea? And if it is a good idea, how big should we make it? How many logic elements should we put inside this logic block? How many inputs do we need to bring in? So what are N and I? And how much interconnect should we put inside the cluster? So today we're going to be talking about, we're not going to be talking about the interconnect inside the cluster that much, but another week or two, we'll get into probably another week. We'll look at some studies that checked exactly how flexible should that local routing be. Okay, so how do we answer this? You really can't answer it analytically. There are too many competing factors. The trade-offs are too complicated. So we're going to have to use an empirical flow. So we take benchmark circuits, so hopefully realistic designs that model the kinds of things we think people will do with this FPGA. We need some automatic compiler. Okay, so a CAD tool that's going to map circuits to the architecture. Then we want that tool or another tool to automatically estimate the area and the delay. So again, we estimated the area by hand last week. We don't want to do that by hand, so we'd like to automate that. And then we get we get architecture efficiency. Okay, so we're going to do this empirically. Okay, so here's my proposed CAD flow. I'm going to take benchmark circuits. I'm going to put them through a logic synthesis tool. Okay, so a logic synthesis tool takes those designs. They've been turned into gates by a process that's called elaboration. Elaboration just converts Verilog to gates. It's basically a template matching operation, so it's not that complicated. It figures out when you write this code, you want an AND gate. When you write this code, you want a flip-flop. This code is a multiplier, etc. So that's happened. And then we go into optimizing gates. So that's a fairly complicated CAD problem. Lots of algorithms that will go off and try to simplify the logic, use fewer gates. We don't really have gates on the chips we're looking at. We have lookup tables. So we need to do what's called technology mapping. So it's another CAD tool that takes those gates and basically tries to pack them into lookup tables. It understands it can only pack, it can't have more than K inputs for a lookup table, so it respects that constraint. And again, there are a bunch of complex algorithms people have developed to try to do this well. Okay, when I'm done, let's say the question I'm trying to answer is just what is the best LUT size? Okay, so I'm not trying to figure out what the best logic block size is, etc. Just best LUT size. So at the end of my CAD flow, I can compute the area by taking the area of a lookup table. So I'm just going to do that transistor level schematic like we did last week, estimate the layout area, or maybe I'll really lay it out. So I get an area per lookup table, and I multiply it by the number of lookup tables. And I know the number of lookup tables for every one of my circuits because I went through a CAD flow that created lookup tables. So I've got that. I also want to estimate my delay. So I'm going to say there's a certain delay for every one of my lookup tables. I can spice my transistor level design to get that delay. And I'm going to multiply that by the depth. So the depth is basically the maximum number of lookup tables that I have in series between registers. So if this is my part of my circuit, lookup table, here's another register, and let's say up here I got another path, so I'm going to look up table here. So that's my circuit. It's not super exciting. 3 registers and 4 lookup tables. What's my depth? Actually, I'll ask you guys this. What is the logic depth of this circuit that I've drawn? So anybody who can figure this one out, type it in the chat. It's a small integer. Yeah, so it's 3. Okay, so the longest path between registers in terms of just counting LUTs is here, and it's 3. So I'm gonna, unfortunately, my Surface is acting up today, which is why I'm trying to do this all on one screen. So apologies if the display is not quite as steady. So yeah, the depth on this is 3. And the area of this by my model is basically, n LUT is equal to 4. Got 4 LUTs, and my depth is equal to 3. Okay, what do you think of my model? Do you like this? I wrote a paper with this. Would you accept it, reject it? What feedback would you give me? So does anybody like this method? Anybody dislike it? If you have any comments, just type them into the chat. Or feel free to speak them out loud if you wish. Okay, so do you consider this a good way to evaluate this question? So the question I'm trying to figure out is, best LUT size. Oops. And the question is this a good flow or not? Yeah, so AG's basically pointed out the key problem with this. The routing area is ignored, and it's also usually large. So last week we went through a calculation of by hand of the logic block area and the routing area per tile, and the routing area was quite a bit larger than the actual logic area. And so a key mistake in my flow here is I actually don't do anything for routing. I basically just completely ignore it. And that's a very bad model because it's not a second order effect. It's a first order effect. So yeah, this actually has been done in quite a few studies of FPGA architecture. Fewer recently, but it's something you want to watch out for because if you do this, it's just not accurate at all. Okay, so it was bad. So to do better, we have to have at least some estimate of routing. And it's hard to be perfect because the perfect estimate of everything involves, building really good CAD tools, doing complete layouts and so on. So we're going to have to make some approximations. So here's my second try. I take benchmark circuits. I run them through a CAD tool that optimizes their gates. Technology maps to LUTs, so same as before, but I've just changed my area and delay model. So my area is now the area of a lookup table, which I got by doing the transistor level design. I know I also have to build K input ports, so meaning K connections to the programmable routing for inputs. So I can work out the area of each of those. The area of an input port. So it's going to be what size of multiplexer did I choose and how much area does that take? And the area of the output port. So we looked at that last week as well. We looked at style of routing where we built it on the multiplexers, and we worked out how many multiplexers we needed to build and how big they were. That's the area I'm really going to need for every LUT. It's not just the area of the LUT, it's also the associated routing. I'm going to take that and I'm going to multiply it by the number of lookup tables that I needed for each benchmark circuit. And my delay, I'm still just going to look for, essentially do counting of levels, but I'm going to basically say there's a delay for a LUT, and I'm going to assume a constant delay for routing. So it's not the same as the LUT delay. It's probably not all that accurate because I'm just going to assume the same routing delay for every connection, and I'll multiply that by depth. So the number of lookup tables in series on my in the longest path in my design. So what do you think? Do you like this flow better? So any comments on this one? So you like it better? Probably you like it better. Anything you don't like about it still? Feel free to jump in with any thought. Otherwise, I'm going to ask Andrew and it will distract him from marking. So it's not in your best interest. So. Okay, so I'm going to, Andrew, what do you think? I wasn't, okay, so Camille said I would add a factor to represent unusable area. What do you mean by that, actually? Is that?
I was more thinking about, so for instance, if we go from 4 LUT to 6 LUT, we're not going to be able to use all of those 6 LUTs. So just a factor that represents how much of, by making these islands, is now unuseful. The more we bundle them together, the more unusable area we have.
That's interesting. So I guess in this example, that's a good insight. Let's walk down that one. So in this example, I'm doing just a logic block that's single lookup tables. Okay, so kind of simpler ones. So the area of a LUT is going to be the area of the LUT I build. So if I'm looking at a 6 LUT, it's the area of building a 6 LUT, whether I use it as a 6 LUT or not. So the fact that I can't always use, the fact that I can't always fully utilize a 6 LUT basically shows up in this N LUT. You know, when I tell the technology mapping tool to map to 6 LUTs, I should get fewer LUTs, but maybe not as many fewer as I would like. Some of the lookup tables that it creates will still be probably 4 LUTs. But I'm still it's important that I pay the area penalty of a 6 LUT, because if that's all I built on the chip, I got to account for that. Does that make sense?
Yeah, that makes sense. I didn't consider that.
Yeah, so I think that basically that's what captures the fact that you underutilize some things. What about routing area? So I've got a model of routing area in here. I'm saying, you know, I've got K inputs and I've got a certain area for routing input, and I got a certain area for the output. How easy is it for me to figure out what those areas are? I guess this kind of tells you, right? It's hard to estimate the routing area. So this is much better because at least I'm trying. And any reasonable guess is better than just assuming it's 0, because that's a really bad estimate. And at least I've captured the fact that it varies, the number of inputs varies with K. Because the amount of, you know, the channel width that I need. So if you think of what I'm building here, I'm building a bunch of lookup tables. My logic block is just a single lookup table, and they're connecting to all these programmable wires that are passing by, because I'm building an island style FPGA. So there are muxes going in. Oops. And there are, you know, muxes that I'm building to drive these various routing wires. But it's hard for me to estimate, you know, what channel width am I going to need? Okay, so that's going to be pretty hard for me to guess very well if I don't have any further, if I don't have any further information. Okay, so what is W? It's hard to say. Yeah, sorry about this. My Surface is actually better at this than the laptop. And that W is also going to interact with how big I make these multiplexers. So, which is going to affect how much area each of these multiplexers takes. So this is a much better model, but it's going to be difficult for me to predict the routing area very well, because it's actually quite a complicated question, depending on how big I make the multiplexers and what the resulting W is. Okay, so we go to the third evaluation flow, which is, this is basically an updated version.
Hi, sorry, here I have,
Sure.
I have issues. Can you please take up issues?
You-
Okay.
I think I'm just going to mute you. Okay.
Okay. Let me get you the other one. Oh, it's running. All right.
I think I can.
That's good.
So Michael, we can actually hear you. I'm trying to mute you, but I'm unsuccessful right now. So, and I don't know why I can't. There, I think I muted everybody now. Okay. Okay, so the actual flow that is used in the Ahmed and Rose paper is basically an earlier version of this flow. This is an more up-to-date version of it. The idea is similar, just the tools have advanced since they did that paper. So they take benchmark circuits. I already mentioned this, elaboration is the first step where you kind of do template matching to figure out what all the Verilog or VHDL means. Then you do logic optimization and technology mapping. So the tools that are used, common tools that will be used for this nowadays are a tool called Odin 2 to do the elaboration, Berkeley's logic synthesis tool ABC to do the optimization of logic and technology mapping, and then a tool called VPR that basically implements the physical parts of the CAD flow and most of the analysis. So the way VPR works is it first packs these little things like lookup tables and flip-flops into the larger logic blocks, places them, so it chooses a location on the chip for every single element, every single logic block or RAM block, etc. Routes between them by using the prefabricated wires and switches and appropriately programming the switches. All of those phases are timing driven, meaning those are all guided by timing analysis. So inside each of these phases, like placement and routing, there are essentially loops where you're estimating delays based on what you've done so far, calling out to timing analysis, asking it to analyze the design with those predicted delays or current delays, tell you what the critical paths are, and then you go back and you optimize some more. Okay, so placement and routing in particular are quite iterative. Logic synthesis, I haven't actually drawn a line here for logic synthesis. So elaboration and technology mapping can be timing driven, but they actually benefit much less. They're early enough in the flow that their estimate of where the design critical path is not that accurate. So most logic synthesis tools don't make much or often any use of timing information. Instead, they basically try to minimize the logic depth, which is what I just showed you a few slides ago. They try to minimize how many lookup tables are connected in series. And they try to do that all over the place because they just don't know where the critical path will be. There have been various efforts to try to make synthesis more timing driven. You can get small gains, but not that much. And it's basically, it's too hard to predict. You're so far, so early in the flow that just trying to minimize the depth of everything, try not to have too many lookup tables in series, is a pretty good heuristic and probably better than really detailed predictions. Okay, so once we go through all of these implementation phases, we basically have to estimate how well would this FPGA work for this particular benchmark. So VPR actually automates basically the transistor level design, or a lot of the transistor level design that we did by hand. Or you can kind of input all of the timing parameters because you've done your own transistor level design, and it'll add everything up and tell you what the area, the delay, and the power are. The area is estimated basically the same way that we did last class. The delay is typically a bit more accurate because you input more detailed models based on SPICE and so on. Okay, so at the end of that, you get out a report on, for this particular FPGA that you were thinking of, how well did each one of these benchmark circuits map to it? How much area did you need? How fast did it run, and so on. So a key part of this flow that's different than Quartus or Vivado. Quartus and Vivado have most of this implementation flow in them, they wouldn't actually output the area, not in like units of silicon. They would output it in resources, but they won't tell you how big the chip is in silicon because they don't consider that any of the customer's business. But the rest of this, a tool like Corticer Vivado would do. The key difference in this flow is this part. So basically the description of the architecture and the process. So you, in addition to saying what the benchmark is, you actually, you say, this is the architecture. So I'm going to use a lookup table of size 6, and I'm going to use 10 of those lookup tables in every logic block. And I'm going to give you a bunch of information about the area of various components of this architecture and the delays and so on. That's a relatively large file, but it still can be written by a person. And then VPR basically takes that description and it builds a really detailed set of data structures that describe the whole chip. So those data structures are gigabytes in size. There'll be every wire and every switch and every place you can put things on the chip. So this step is something that's kind of unique to architecture evaluation tools, where you go from something a human can write, kind of the basic idea of this architecture, and you automatically create a really detailed representation. In Corticer Vivado, basically this really detailed representation, this architecture database, would be read in from disk, and it was created typically from the actual layout of the FPGA. It would take an incredibly long time to produce such an architecture database for every one of the chips that you were trying to evaluate when you're doing an architecture study. So instead, as I said, we use this architecture generator to bridge from this human readable architecture description to this architecture database that is suitable for a CAD tool. Okay, so that's the basic idea by which most of the architecture studies I'm going to show you work. They use a CAD Flow, either that exact CAD Flow or one relatively similar to it, to evaluate different ideas. Okay, so let's talk about the first paper, which looked at how do we choose a good lookup table size and cluster size. Okay, so is there a bunch of figures grabbed from that paper? So one of the first things they looked at is that, okay, let's just look at lookup tables and registers. This is my basic logic element, and let's not put them inside of a logic cluster at all. Let's just say this simple logic element is my whole logic block. So in this case, I got 4 inputs, 1 output, plus a clock input, which is typically put on a special network, so it's a bit different. And what they showed by going through a CAD flow very similar to what I just showed you is the area per cluster. Well, that comes from basically transistor level design of the lookup table and of the routing. And they use the CAD tool back here. They use basically the routing phase of this CAD tool to figure out how wide they need the channel to be. So this area per cluster that I'm showing here includes the routing. It's not just the area of the lookup table. And to get a good estimate of that routing area, they need to know channel width, as well as how they're going to build the routing. So they get that from the CAD flow. They run a whole bunch of benchmarks through and they vary the channel width, seeing how wide does the channel have to be for each of them to route on this architecture. And from that, they pick a channel width. They actually pick the average plus some amount, and they can calculate the area per cluster. The other thing they need to know is how many clusters were used on average by the CAD flow. So as they go from small lookup tables to big lookup tables, the area per logic block, which is just one lookup table, gets bigger. So going from a small lookup table to a big lookup table, the area per lookup table gets bigger. That makes sense. But the CAD flow is able to make good use. See if I can get a different color here. Is able to make good use of that. So basically, they need fewer LUTs. As they use more and more of them, or as they make the LUTs bigger and bigger. And they don't have a separate figure that shows just for for one LUT per cluster what this turns into in terms of total area, but it shows up as a line on some of the later charts. And basically, the best trade-off is somewhere in the middle. You don't want really big LUTs. You don't want really small LUTs. And so does that make sense? So basically, when they go from a 2-input LUT, they need, on average across these designs, over 4,000 lookup tables to implement them, each design. And when they go to a really big LUT, 7 inputs, that drops to more like 1,300. So there's a big reduction in how many lookup tables they need. But at the same time, the area goes up a lot. So they go from, in this kind of layout estimate of how many minimum width transistor areas you need, they go from about 100 minimum width transistors to implement a 2-input LUT plus all the routing it needs to something about 16 times that size for a 7-input lookup table. So here's a skill testing question. So we looked at lookup tables and how their area grows as you increase the number of inputs, K. And we said it's exponential, right? It grows as 2 to the K. I'm going from K equals 2 to K equals 7. So that's 2 to the 6th times bigger, okay? And, or sorry, 2 to the 5th times bigger, which is equal to 32. Okay, so if I expect the lookup table size to grow exponentially, going from this spot to this spot, I would expect it goes up by a factor of 32 in area. But if I actually look at this axis on the left, I actually only went from about 100 to about 1,600, so a factor of maybe 16. So why? Why when I predicted that the SRAM cells and the number of transistors in a multiplexer both would have gone up exponentially with K, that would lead me to believe that it should go up by a factor of 32. It actually only went up by a factor of 16, which is still a lot, but why? So if you got an idea, either unmute yourself or just type it into the chat. Yeah, so there's other stuff. So Gil said the size includes some non-multiplexer factor didn't scale as much. I mean, there was that output driver, so that's a little bit of area. There's a flip-flop, so that's some area. So there's some constant area, so that's true. Larger LUTs needs less routing between them. Yeah, so basically there's some constant area. That's one part of the answer. Whoops, sorry. The other part of the answer is routing area. So routing area is big, and it actually does grow as you increase the number of lookup tables, but routing area basically grows, whoops, sorry about that. Routing area basically grows linearly with K. Roughly proportional to K. Whoops. Because the number of inputs is only growing linearly with the lookup table size. So I have to build more routing input ports. If you go back to the analysis we did about what first order analysis of W, we said W is proportional to lambda R bar over 2. Okay, R bar is the thing that's really hard to estimate there. How far does the average signal get routed? But basically lambda is number of inputs. So we expect our channel width to go up approximately linearly with the number of inputs to our logic block, which is K. We also expect, we also know that the number of input muxes is going to go up linearly because we're only going to build K of them. For both these reasons, routing area is going to go up approximately linearly with the lookup table size. So we have to add that in. And the overall curve is basically a bit more complicated. Still obviously has an exponential component, but we don't see that 32 times growth. We see only 16 times because of the routing. Okay, hopefully that makes sense to everybody. When you take this trend and multiply it together, so I just take the number of lookup tables that I need times the area of the lookup table plus the routing that comes along with it, Ahmed and Rose get this figure. So basically there's a broad minimum. in the 4 to 6 LUT range, with 5 being a little better. But there's a pretty broad minimum. You don't want really big LUTs. You don't want really small ones. And so the basic reason is the small ones wind up using, they're not that much smaller because they have a lot of routing that comes along with them. And you need a lot of them. If we go back to this slide. So we need many more of these small LUTs, and because they're smaller, but not as small as we'd like because the routing that they need, that's an inefficient architecture. On the other hand, if we go all the way out here, so I can get a different color again. Sorry, my apologies. I'm still figuring out all the weird things that PowerPoint does based on where you touch. Okay, so let's see if I can get rid of that. So if we go all the way out here, that lookup table is really big. That's this area up here in terms of area. So those lookup tables are just very large. And while we do need fewer of them, it's not enough to compensate. Okay, so we get this broad minimum. And if we do this for delay, we wind up with the number of BLEs on the critical path. So the number of LUTs that we need to have in series on our critical path goes down. So that's what this curve on the left is. So this curve is how many lookup tables do we have in series? Okay, and it's clearly going down as we make the lookup table bigger. And that makes sense. Look, each lookup table captures more logic. So not only do we need fewer of them, we don't need as many of them in series. Okay, so for delay, what we care about is chains of lookup tables. And that's what this is showing. That number of chains goes down from, for the average circuit, from about 26 lookup tables in series down to, by the time we get to 7 input lookup tables, about 5. So a big reduction in logic depth. Each lookup table gets slower and it gets slower approximately linearly, which we analyzed a couple of weeks ago. The number of levels in the multiplexer tree inside the LUT goes up linearly as you increase the number of inputs. So every input adds one more level in the multiplexer tree. So it makes sense that the delay of the lookup table goes up linearly. This doesn't speak to routing delay. So the routing delay is also changing. It's not on this figure, but they take it into account in their final results. Okay, so that was looking at just single lookup tables. But they don't want to look at only single lookup tables. For all the reasons we talked about before, these logic clusters are interesting. So they want to now take a lookup table, a flip-flop, and basically put it inside of a larger logic block, as we've described before. And that logic block, shown here, is going to be embedded in an island-style FPGA. So they've got some local interconnect and some LUTs that makes very small hierarchical FPGA, and then they make an island-style FPGA by replicating those across the chip and putting, wiring segments and programmable switches in between them. So to evaluate what's best, they want to look at 3 different parameters. They want to look at the area, total area of the chip that they need to implement their benchmark circuits, the delay, so the average critical path delay, the frequency limiting delay across these benchmarks in each chip that they're evaluating, and the product of those 2 things, the area, so the area delay product. So this again is maybe a comprehension test. Why? Why do they want the area delay product? Is it just a convenient way to combine area and delay, or does this have any more fundamental meaning? So it is a convenient way to combine them. So that is one answer. But if you're trying to get the most processing out of a certain unit of silicon, you can basically get more work done by reducing area, which means you can replicate more LUTs or logic blocks, more functional units. Yeah, so as Camilo said, this gives us an estimate of the performance of the chip. Or we can reduce the delay. Okay, so reducing the area would allow us to have more parallelism in the same area budget. Reducing the delay just allows us to clock it faster. The area delay product, therefore, is basically 1 over throughput per unit of silicon. So it is an estimate of the performance of the chip. And industrial FPGAs, for the low-cost FPGAs that I was part of the team that architected at Altera, so those were the Cyclone FPGAs, we would basically optimize area delay product. Or sometimes for those ones, we may optimize area a little more. So area delay product, or maybe, area to the 1.2 times delay. For the higher performance chips, the Strat-X chips, we'd push it a little more towards delay. So it might optimize area delay squared. So that's when you're trying to make 2 different chip families and you want them to be different. You'll optimize one for area more and delay some, and the other for delay more and area some. If you're trying to make one family of FPGAs and just get the most throughput per silicon, then this is the most logical thing to optimize, area delay product. In order to evaluate, full chips, including their routing, Ahmed and Rhodes have to pick a routing architecture. And the ideal would probably be that for every single architecture they look at, they also go off and evaluate what are all sorts of different routing architectures and pick the one that's best tuned to that logic block architecture. But it's just too much work and too much compute. So that's very hard to do, to kind of simultaneously explore all parts of an architecture. So what they do is pretty reasonable. They pick what is known to be a pretty good routing architecture. So they say all the routing wires are length 4. So they go past 4 logic blocks before they end. They have to choose how this local routing works. Whoops. Okay, so there's local routing here. They have to choose how that works. So they say it's going to be a full crossbar. So they can choose. So basically every one of these muxes is going to have n plus I inputs, because it can choose between n outputs that were generated in the same logic cluster and I inputs that came in. And their wiring, they make half out of pass transistor switches and half out of tri-state buffers. And they have to choose a process technology. So this paper is a classic one, but it was done a while ago. So they use 180 nanometer process technology. Okay, so they have to estimate, they have to basically do a transistor level design of the whole thing so that they can estimate delays. So the signal path that they essentially have to find the delays of every component, and it's also kind of illustrative to think what's going on as circuits are mapped to this architecture. So the signal path into and out of a logic block is, you've got island style routing. So you come in, you've got some routing wire segment that was driven by, some logic block that's potentially far away. From that routing wire segment, they go through a buffer, then into the input connection block mux. So this is this routing input port. So they have a mux that allows them to choose between a bunch of different routing wire segments, which one's going to make it into a certain input. Then they have another buffer, because they're going to be driving a reasonable amount of capacitance. This is their local interconnect. So local interconnect are these muxes with n plus I inputs. They have a whole bunch of them. So every single input to a lookup table has one of these multiplexers in front of it. Then they have their lookup table. The lookup table output can be registered or it can bypass the register. And then they have a couple different buffers. They have a buffer here to drive a signal back into the local routing in case it wants to be reused by some other lookup table in the same logic block. And they have another buffer that drives it out to the programmable routing. To get to the programmable routing, they have to go through a programmable switch. So they have pass transistors here that are controlled by SRAM that can let them get to various routing wires depending on how they program them. So that's how they built this whole thing. The circuit design is pretty reasonable. There's one thing that actually is quite hard to do. This first buffer, let's see. This first buffer actually doesn't exist in commercial FPGAs because it's just, there'd be too many of them. There are a whole bunch of them and they're really hard to lay out. So generally, you don't wind up with this buffer. You go straight into the multiplexer. That's a sort of a small approximation error in the circuit design, but I don't think it affects their conclusions very much. Okay, so they also have to decide, so they got lots of choices to make. So we talked about the choices they made for the routing architecture. They also have to decide how many inputs are they going to use per logic cluster, this number I. They'd like to make it as small as possible. Let me go back and look at this again. If they make I smaller, that's basically here, this how many inputs they have. They don't need as many of these input connection block muxes. And also the local routing muxes get smaller. So they kind of win in two different ways if they can make I smaller. They're going to get rid of a bunch of multiplexers to connect in from the island style routing, and they're going to make their local interconnect smaller too. So they'd like to make that small. But obviously there's a limit. If you just make it too small, you'll find that you can't actually use all these LUTs, that they need more inputs than you can get them. So your architecture is not very efficient because you got a lot of lookup tables that your CAD tool can't actually use because it can't actually get inputs to them. So that would be kind of wasteful. So what they do is they basically use their CAD flow. They use the first phase of it, the packing phase, to determine how many inputs they need to use 98% of their LUTs. Okay, so they're allowing 2% of them to be unused because maybe there are certain logic blocks that are just trying to use, just really hard to, they want a ton of inputs. So maybe being able to fit all of those, pack those logic blocks to 100% usage is just going to cost too much in terms of inputs. So they make this decision of they'd like to use 98% of their LUTs, and across their benchmark suite, they evaluate how many inputs do they need to the cluster in order to make that happen. And they're doing this not just for one logic block size, they do it for a bunch of different logic block size. So this is cluster size n, how many lookup tables per logic block. And this figure comes from another paper. This is a paper I wrote earlier, introducing these kind of logic clusters. And it was done for only lookup table size of 4. So this is lookup table size 4 data. And there are two curves here. They're on average, how many inputs do we need? So that's this curve. How many inputs do we need per logic block? And as you'd expect, it goes up gradually as the logic block gets bigger. But even if we have 16 4 LUTs, the average number of inputs you need is only around 18. And then the solid line is how many inputs did you have to build into the logic block so you can use almost all the LUTs almost all the time. And that's a higher number. By the time we get to 16 lookup tables in a logic block, we need to have about 32 inputs. So quite a bit more than the average down here. And the reason we can do this is basically this local interconnect. It allows us to share signals. So we can bring, let me see if I can clear some of the, we can bring a single signal in. Like this signal. And so we bring it through that mux. And then this local routing allows us to take it into maybe this LUT, but this signal also goes to all these other muxes. So it can go to another LUT down here and so on. So the local routing allows us to bring a signal in once and use it many times. It also allows us to take signals that were generated, maybe down here by a certain lookup table and bring them back up here and go through a mux into here. So we can reuse some of our outputs. Okay, so those are the two reasons that we don't need to have, we can reduce the number of inputs per logic block below, in this case, 4 times n, which is what we'd need if we just had to bring in every conceivable input a LUT might ever want. And in the Ahmed paper, they basically come up with a rule that they observe by making a bunch of graphs like this. They find the number of inputs they need, which is basically this curve. How many inputs do I need for 98% logic utilization? Is k divided by 2, k is the LUT size, times n plus 1, where n is the number of LUTs. Okay, so that's less than K times N, which is the number of inputs on all the LUTs that are inside of the logic block. So they did get some sharing of inputs, some reduction of the needed inputs, which is good. Now we studied rinse rule, right? And just to remind you, rinse rule is the number of terminals in some piece of logic is proportional to the amount of logic, so gates, or in this case, well, it's gates to some rent exponent, which means it's proportional to n to some rent exponent, right? Because n is the number of LUTs we put in this. So does this line up with rinse rule? Okay, so they've empirically measured this. They ran their CAD flow. They found I can get by with this many inputs per logic block. And I mean, basically I can say that the amount of logic is proportional to like K n to the P. So what does this imply P is? Or does this make sense? Does this line up with rinse rule? So we have these two different trends. They find that the number of inputs they need, which is terminals, okay? So, you know, inputs is, I mean, it's only the inputs, but you can apply rinse rule either to all the terminals or just all the outputs and all the inputs. It'll work for any one of those things. So my inputs is going to be proportional to the amount of logic to some rent exponent P. My amount of logic is K times N. So what does this imply? What does their equation imply the rent exponent is? So you just have to figure out, like, how is it varying? What P do you need to make this equation work? Yeah, so basically this equation actually implies, so sorry, this is need to find a highlighter here. Let's see, let's not do that. Let's see, where are we? Yeah, so this equation, we can see that our inputs are growing linearly with n, which is basically proportional to logic that we put inside of a logic block. So this implies that they're getting a rent exponent of 1, which I said was pretty bad. Okay. Whoops. Let's get rid of that. Or it seems to. So does this imply that their CAD tool is really bad because it's getting a rent exponent of 1? So this might be a hard question. So is there anything that I'm missing here? So up here, I've got these two different curves. I got the average inputs used right there. And I've got the kind of the maximum, right? Or almost maximum. And they're setting the number of inputs by the almost maximum. Rinse rule actually is predicting the average. So if I look at their average, you can see that the curve is bending some, right? So it's not actually going up linearly. If it went up perfectly linearly, this point here is probably about 6 or 7. So if I go up 4 times that, I would be, let's see if I can do this math correctly in my mind. So a linear increase from that would be probably around here, okay? So that would be rent exponent 1 for this average inputs used. And you can see the curve is actually bending. So the rent exponent is somewhat less than 1, okay? So it is less than 1. So that implies their CAD tool is not so bad, right? Maybe they could still do better, because if I fit a curve to this, the rent exponent looks like it might be 0.75 or 0.7. So it doesn't look fantastic, but it's a lot lower than 1. So yeah, the target they've set for themselves of that they can get to 98% logic utilization is actually a fairly hard one. And and they're using a packing flow that really tries to shove as much into a logic cluster as it can. So this input count is, potentially a bit high. Like there are studies that have shown you can reduce this if you're willing to accept, less than 98% logic utilization. Anyway, but it is also true that rent's exponent predicts the average, and the maximum tends to be worse than that. So they wind up with their inputs not dropping as required inputs not dropping as quickly as you might hope if rent's row was really helping you a lot. Actually, I would see a question from Monty of does the delay change? We'll go back here and let's see if I can erase some of this. So your question is does the delay change if an input is used in more than one LUT? Not very much at all. Okay, so the reason it doesn't change very much is these buffers. So this architecture is pretty heavily buffered. So the action of basically selecting the signal to go through this mux turns on a pass transistor. It does expose a little bit more capacitive load to this signal, so it does slow it down a little bit. And the more routing muxes that you do that in, the more capacitive load you expose, and you slow down this buffer. But it's a pretty small effect because this buffer is built to be reasonably powerful, and the pass transistors are not that big, so they don't expose that much extra load, especially because we have another buffer here. So FPGAs tend to build a lot of buffers to try to isolate capacitance. So sending this signal through multiple multiplexers by turning on multiple pass transistors does slow it down a little bit, but not much, because most of the capacitance is actually the wiring. And we have these, a powerful buffer before and a buffer right after the mux to kind of make sure we don't add some more capacitance to this pass transistor inside the mux that it has to dissipate. So the effect's pretty small. So it's a good question. Were they too aggressive with assuming 98%? It may be a bit conservative anyway. There are some studies that show that if you make your cluster a little less aggressive, you can push this input count down more. Okay, so let's keep going and look at, what do they find from this overall CAD flow? So I'm going to show you a whole bunch of graphs and try to, try to interpret what they mean. Okay, so this is basically area on the y-axis and lookup table size on the x-axis. Okay, so small lookup table of 2, big lookup table of 7. And we're changing the logic cluster. And here they're showing how much area is in this local routing. Okay, so inside there. Well, it's actually not just the local routing, sorry, I shouldn't say that. It's actually how much area is in the local routing plus the LUTs, everything that's inside the clusters. So it's not including the routing between the clusters, it's everything else. So cluster size of 1, we kind of already saw. This is a single lookup table, no local routing, and it's this line, and it's the best for minimizing the area of the actual logic cluster because we're building as little as we possibly can. As we go from a lookup table size of 2 to 7, we kind of get the curve that we already have seen, right? Gradually it goes up. As we increase the n, the number of lookup tables we put inside of a logic block, we get a gradual increase in area, no matter what the lookup table size is. And that makes sense because we're grouping a bunch of lookup tables together with local interconnect. Basically, this is showing us the cost of the local interconnect because this is all just the area in the cluster. So the biggest one is cluster size 10 up here. So this all makes sense. Let's see. I think, so Andrew, I see you have a question of like, if 98% utilization is very aggressive, why build that many anyway? So what do you mean by that? You mean why build so many LUTs in a cluster if you can't use them all? Is that your question?
Yeah, kind of. So if most of the common benchmarks cannot get the best use out of that many LUTs, why build that many anyway? And
well, I guess the way this is done, they can, right? So at 98% logic utilization, it means most of your logic blocks are packed all the way to be full. Does that make sense?
Yeah, but
if the curve for 96% was here, and I just drew that line in, then the area savings between these two curves might pay for adding 2% more logic or more to the design, to the chip. And if that's the case, then you'd be better off to say, look, it's okay to only use 96% of them. You know, most of the logic blocks will still be full, but there'll be some that I can't fill completely because they're from parts of the circuit that don't share as much, you know, they're kind of more irregular. They don't share as many signals. These lookup tables are kind of hard to pack. And I wind up with some logic blocks that I just can't fully pack. If that doesn't happen that often and I saved a fair amount of area, it may actually be a better choice because I could just build more logic blocks.
I see. So in an actual device that is being produced, they always try to guarantee that all the logic blocks are usable. That's how they decide how many input ports they put in the architecture.
Yeah, I mean, I can tell you what we did at Altera, which was actually relatively close to this. We went pretty high in terms of we wanted to make sure you could use all the logic blocks most of the time. Does that make sense?
Yeah.
You don't want this number to be really low. There's some academic studies that say you could save area a lot if you basically push this a lot lower. It's hard for customers to deal with because it's very hard for them to say how much can I actually, for my design, how much can I fit in this chip? Does that make sense?
Yeah.
So, you know, in the end, this is not an unreasonable way to choose how many inputs there are. But there's another way you can do it, which is basically you just change the number of inputs per logic block for every single size and see what's the minimum area solution, like what chip is the most efficient. And that chip might only hit a 96% or 95% logic utilization on average. You know, maybe some circuits is higher, some is lower, but it was able to make the logic blocks so much smaller that it was better.
I see.
But it's a lot of computation. And so they basically, the authors of this paper take this shortcut, which is not an unreasonable shortcut, but it may result in them saying that they need a few more inputs than they really need because they didn't explore sort of more spaced out options. Does that make sense?
Yeah.
But I guess I'm not saying that it's a really wild and crazy thing to do that's really wrong. So, okay, so this curve kind of shows what we'd expect. And if this was the end of it, you would just say, well, these large lookup tables and these, oh, and actually the last thing I should say is this is not the area of just one cluster. This is the area of all the clusters you needed in the whole design, okay? So if there was no routing between clusters, this says use really small lookup tables and use really small logic clusters. But obviously there is routing between the logic blocks too. Okay, so if you look at the routing between the logic blocks, so this basically chart is showing all the other area. Okay, so we're ignoring what's in the logic blocks, just taking the wiring between them and working how much area we need there. And basically the trend exactly reverses. So a smaller lookup table, so lookup table of size 1, and a small logic cluster, so we don't have any local routing, we just put one LUT in a logic cluster, is now the worst. We have to route tons of signals between lookup tables because we have so many of them. We have no local interconnect, so everything goes in the general interconnect. So our routing area between logic blocks is very high. As we make the lookup table bigger, we don't need as many. We don't have as many signals to route between them. So our routing area goes down between the logic blocks. And as we go to larger cluster sizes, the routing area between these logic clusters also goes down quite a bit. So, so basically this is cluster size 1 here. This is size 2 here. Let me change my color of my pen. Once we get up to some really big ones, it looks like it's kind of flattening out. It's not as clear there's a gain, but somewhere this is like 8 or so down here. So big logic blocks do save a lot of routing area between them. Okay, so you kind of have to put those two graphs together to see what the overall picture is. And this is on the y-axis is the total area averaged across these benchmarks. And on the x-axis, we have the lookup table size. And we're showing logic clusters from size 1 to 5. Okay, so what do we see? So we see that, whoops, let me see. I'll draw it on here. I couldn't remember what animations I had in here. there's a net gain to using these logic clusters. We do see from a logic cluster of size 1, if we didn't have any local interconnect, just size 1 logic clusters, the best LUT size was 5, so reasonably large LUT. If we actually go to a logic cluster of size 2, it gets worse. Any ideas why? Why is a logic cluster of size 2 worse? But then as we go to 3, 4, 5, it gets better. We start saving area. This might be a really hard question, so maybe if nobody can answer it, I'll just move on. Why do you think logic cluster of size 2 gets worse and then it gets better after that in terms of area? Yeah, it's maybe too hard a question. Basically, you add the local interconnect in. Yeah, so actually people guessed this quite well. Immediate addition of muxes. That's basically when you go to a logic cluster of size 2, you add an extra layer of muxing into your logic block, but it's still a pretty small logic block. With only 2 LUTs in it, you don't capture that many signals inside the logic block. So the local interconnect doesn't actually pay for itself. When you go to larger logic clusters, the local interconnect is better able to capture signals and it pays for itself. So that's what's happening here. This is the other half of the story. It's basically the same figure, but it's just the larger clusters now, 6, 7, 8, 9, and 10 LUTs. And 10 is up here. Okay, so 10 is actually not doing quite as well in terms of area as logic clusters that are a little bit smaller. So there's kind of a broad minimum in area for LUT sizes between 4 and 5 and logic clusters between about 6 and 8. So why does a logic cluster of size 10 start to do worse? Okay, so we said logic cluster of size 2 did badly because we added local routing and it didn't capture enough signals, didn't pay for itself yet. What do you think is happening with a logic cluster of size 10, which is starting to do worse than the sort of more moderate size clusters? Yeah, so because of the cost and the area of the inputs, it's exactly right. Like the local routing is getting very expensive. So local routing is being built as a crossbar, right? So we have n, well, on every single LUT input, so on k times n LUT inputs, we have a mux, which has n plus I inputs. So if you multiply through the area of this, basically the number of muxes that we need is growing with n, and the size of those muxes is growing with n, and the area of a mux actually grows linearly with the number of inputs. What that means is that we've got order n squared area for the local interconnect we've chosen. It's basically a full crossbar for a sufficiently large cluster that eventually starts to kill you. So even though we're capturing more and more connections inside the cluster, we don't need as much routing outside the cluster. This quadratic growth eventually kills us. Okay, so we want to kind of be balanced. Moderate but reasonably large LUT sizes and cluster sizes are good. Okay, what about performance? So we don't care just about area. We care about how fast the thing is too. And this is basically the total critical path delay averaged across those benchmarks. So the speed limiting path from each benchmark, average how long it is in nanoseconds. On the x-axis, we have the LUT size. We're going from small LUTs here to big ones there. And again, we're doing this for a whole bunch of logic clusters. So this is LUT size of 1. And down here is a LUT size, or sorry, cluster size of 10. So this is 1 LUT per logic block. This down at the bottom is 10 LUTs per logic block. And we can see that the local interconnect, by capturing some connections inside the logic cluster, those muxes are pretty fast. They're faster than going out to the island style routing, which implies multiple switches to get to the destination. So even at a cluster size of 2, it speeds things up. And if you keep going bigger, it keeps speeding things up. Now, eventually, the local interconnect starts getting slower. So you can't, because the muxes keep getting bigger and your delay starts to increase inside the local interconnect, but you can go pretty big. So basically this, for delay, it favors larger lookup tables because the largest lookup tables are actually the fastest. And it favors, pretty big logic clusters because they're also getting faster. Although they do start, Yeah, well, I won't say any more on that. Okay, so we put all this together, an area delay product, we just multiply all this data together. And this is, essentially our metric of silicon efficiency. So what do we see? Whoops, don't have any animation on there either. I guess again, we have, well, lookup table size, or cluster of size 1. So this is n equals 1, and it's not as good. Okay, so logic clusters are definitely a good idea, not just for delay, they're also good for area delay. This is a cluster size of 2. It's a bit better, but not nearly as good as some of the other ones. So reasonably large logic clusters are good. On this figure, basically 4 to 10 all look pretty good. And then there's a pretty broad minimum in LUT size. So from about 4 to 6, it's not that strong a difference in area delay product. So pretty broad minimum. So to summarize that, as we increase the LUT size, we capture more logic in each lookup table. We don't need as many levels on the critical path, but each lookup table gets slower. It gets slower linearly in K, and it takes more area. And that one is fast. That's exponential in K. Cluster size, as we make it bigger, we reduce the general routing demand. So that saves us area in the general routing because we can use a smaller W. As it gets bigger, we capture more connections on the fast local routing. So that's good. The area grows as n squared because we got a full crossbar, so we can't go too big on n. And the local routing delay also, the delay of the local routing itself increases with n, roughly linearly, which means there's another reason you can't make n too big, because eventually your local routing would get slow. Okay, so we needed, because of these complicated trade-offs, we need full CAD flow and detailed circuit models, which is exactly what this paper did. They found the best delay is for really big LUTs, K equals 7, but they're pretty inefficient in area. And they found large clusters are also good for delay. So, but the best area, they found the LUT size of 4 was best for area, and still reasonably big clusters, 6 to 10 LUTs. If you typically want both these things, so the best area delay is a LUT size between 4 and 6 and a cluster size between 4 and 10. And while there's this broad range in terms of best area delay, they're not all the same. So a 6 LUT is faster. Okay, so they showed it was 14% faster than a 4 LUT, but it costs 17% more area. So while all these LUT sizes they showed were reasonably close in area delay, the bigger ones were faster, the smaller ones were more area efficient. And if what you cared about was the product of those two things, then it roughly canceled out. Okay, so with that, I'll be on the line, but basically we can take a break for, how about till 5:40? So if you have any questions, ask them during the break, and then we'll talk again at 5:40 about the second paper.
Why 2? Why not just 1?
That's a good point. Yeah, you could almost do it with 1. They built 2 because, okay, this is the next thing I was going to talk about. But basically, if you only wanted to replace the registers with a cheaper thing, then you probably only need 1, right? Because you could say, I only need 1 clock per logic block, and that's not too restrictive. If you widen the pulse, then you actually can allow a signal to arrive a bit late. Okay, so an edge triggered flip-flop, your signal has to be, let me change my pen color here. Whoops. An edge triggered flip-flop, I think I've accidentally turned on, sorry about that. Let's see. Okay, let me try that again because I think I turned on annotations, so I don't really want that. Okay, an edge triggered flip-flop. And let's see if I can get a pen here again. You basically need the data to be stable before the clock edge. Okay. Yeah, let's see if we can do an annotation here. Okay. So your data has to arrive before that clock edge. With a pulse latch, if you actually extend the pulse, so you intentionally make it a bit wider. Okay. So you program in a longer delay into this circuit. And this circuit actually is a programmable delay. That's what these are two SRAM cells. This is a chain of inverters. And basically you can pull off at various points after one inverter, two inverters, three inverters, so on. So based on what I program in here, I actually can get a version of the clock that's either more delayed or less delayed. Does that make sense?
Yeah, it does.
Okay, so what that allows me to do by delaying the clock more, I basically, when I invert it and AND it, I'll get a wider pulse. Okay, so they have the ability to, program in a wider pulse. Okay, now why would you want to program in a wider pulse? Well, as I said, on an edge triggered flip-flop, my data's got to get there right like before the edge, or I have a timing violation. With this pulse latch, the data can actually arrive anytime during the pulse, and it will actually make it through to the downstream logic. That actually means my data could arrive a little bit late, and it's still okay as long as the downstream logic has some timing slack. Does that make sense? So yeah, I've got a register here. So let me see if I can write on this with a little more neatly. I've got a register here. It goes through some logic, goes to another register, and it goes through some more logic, and it goes through another register. Okay. And let's say that the delay of this whole path is currently 4.5 nanoseconds. Yeah, let's say it's 4.5 nanoseconds. And let's say the delay of this whole path is only 3.5 nanoseconds. And let's say that I want to hit a clock frequency or a clock period of 4 nanoseconds. So I actually have some extra time on this side, but I have negative slack on the left-hand side. So, traditionally what you try to do is you try to reduce some of the routing delays and make it work. But they now have an additional option of they can actually widen this pulse by 500 picoseconds. Does that make sense? If they widen the pulse by 500 picoseconds, this register, which is not really a register anymore, it's a pulse latch, will actually accept data all the way up to 4.5 nanoseconds, right? The clock period plus 500 picoseconds. Now that means the data actually arrived late to the downstream logic, but that's okay because it had 500 picoseconds of positive slack. It can tolerate the delay. Does that make sense? Oops.
Right.
So the main reason I think that they put two of these clock pulse generators in there is to allow them to program in this time borrowing more flexibly. They can choose two different settings of time borrowing within the same logic block, which allows them to use this optimization more because not every register has to pick the same setting. Does that make sense?
Yeah, it does.
There is a cost to this, by delaying this signal. Well, there's two costs. By widening the pulse on this register, I basically, when I timing analyze it, I have to assume the data comes late, okay? Which means this downstream logic better have some, whoops, sorry about that, better have some timing slack. The other cost is that my hold time gets harder, right? I have to make sure that there are no paths that could get through this register in that 500 picosecond period. Like there's no other logic that's really fast up here. They could have a delay of say 400 picoseconds to the register. Sorry, this is getting very hard to read. Let me erase that. If there's some other logic up here, and let's say, comes from some other register, and it turns out that this path is really fast. Let's say that path is only 400 picoseconds. That's going to be a problem, okay? Because this is actually going to let the clock arrives, this data changes, it actually can make it through this pulse latch in that 500 picosecond window where it's accepting new data and make it to the downstream logic. And that's a hold time violation, right? That basically means I got new data. My data made it through 2 stages of pipelining in 1 clock cycle, which is never allowed. Does that make sense?
So yeah, so would the flip-flop be using 2 clock signals simultaneously?
So no, every flip-flop has to pick one or the other. Okay, so you make two of these pulse generators in logic block. You basically have generated 2 signals that kind of are broadcast through the whole logic block, and every single register gets to pick one or the other. Okay, and the basic reason is that different registers might want different amounts of what's called time borrowing, what I'm describing here. Or sometimes you do wind up with 2 clocks in a single logic block. You know, it can be useful occasionally to have that because you've got some clock crossing logic. Like you do actually have 2 different clock domains that are interfacing, and putting those 2 sets of registers in one logic block can be useful. So it does happen sometimes. The more important reason is probably to allow different time borrowing settings for different registers in the same logic block.
Okay, thanks.
Anyway, the assigned reading is StratX 5, so you'll read more about this, and I'll talk a bit more about it next week, like the about time borrowing and so on. Okay, and let's see. So I see some other questions here. Do they really need 2 for logic blocks? Yeah. Okay, so we just talked about that. Could you explain about restricted F max, which is less than absolute max, and some that's due to minimum pulse width? Does it relate to this? Let's see if I can bring up a. Yeah, so the restricted F max is basically device limits that are inside of a block. Okay, so let's see if I can bring up a whiteboard and share it. Okay, let's see. Let me clear all these annotations. All right. Okay, so restricted F max. Oops. Yeah, let's get that whiteboard back. Okay, hopefully you can see this. Restricted F max is basically paths inside a block. So we might have a DSP block, for example, and inside it, it has pipeline registers and and a multiplier. And so there are some limits to how fast can a DSP block run, no matter what you do outside of it. So you can get a restricted F max due to, for example, a DSP block. Whoops, where did that go? Which is basically how fast can this thing go. There are also restricted F max for the actual clock networks. The clocks, if you try to send an infinitely fast clock through an FPGA, there are these big clock networks that distribute it, and eventually they can't actually toggle fast enough. So that's another restricted F max. There are restricted F maxes on certain IOs. So depending on what kind of IO you use, there's a certain maximum rate at which it will toggle before the signal is too degraded. So when you get a restricted F max, is one of those things. The most likely one you're going to get in lab 2 would be a restricted F max due to a path inside of a DSP block. What can you do about it? It does limit your F max, so you have to take the lower of the 2. You can look at the data sheet for the chip and see, can you turn on more pipelining inside of that block, like the DSP block? Can you use it in a different mode? Basically, is there any mode where it's faster? And generally, the fastest is going to be turn on every pipelining register that you can inside this block. Does that make sense?
Yeah, thank you.
You're welcome. Yeah, Camilo, you're asking about if you use these pulse latches and time boring, you'll have to worry more about hold time violations, and that's true. The CAD flow does get harder. The tools analyze for the hold time violations. The reason pulse latches have become popular in FPGA architectures is they do present this trade-off of, because there's only one latch instead of two, basically the sum of T setup plus T clock to out, basically the delay to get through the register. That's basically the delay before the clock edge and the delay after the clock edge. The sum of those two things is essentially the delay through the register. That gets smaller. Okay. Sorry, this is making me miss my surface. And I guess I have to do this without touching the screen. All right, so that gets smaller. But the hold time does get bigger. Okay. For FPGAs, it's not a bad trade-off. Also, the register area, because you're only building one latch instead of two, gets smaller. So as long as you don't have to build too many pulse generators, you can amortize those using the technique we just talked about, then you can save area. And FPGAs have a lot of registers, so it's more important to save area on them than it would be in a lot of types of devices. In the hold time, what you can do is, so you've got some paths that are too fast. You've got a register, not much logic feeding another register, and you've got to worry this pulse latch doesn't have as good a hold time, so maybe you get a violation. This path is too fast, and data runs through. This is where the fact that you have this FPGA routing that's relatively slow becomes helpful. If this is too fast, you can tell the FPGA router to basically put an extra wire in. So go up here, go through a routing mux, come back down, now go in here. And that increase in delay hopefully resolves your hold time violation. If the hold time violations there are too many of them and they're too big, then the router's going to have trouble, right? It's going to have problems putting enough extra routing into such a large number of signals that it just can't fix all these problems without running out of routing. But it can fix a moderate number of hold time problems. So this is a case where the relatively slow FPGA routing, where you've got all these multiplexers and so on in it instead of just wires, actually helps you because you're trying to now slow down some paths. And usually you have some extra routing available because you had to build a certain channel width for your difficult to route circuits. So for the majority of circuits, you've got some extra wiring available. Does that make sense? It definitely does put pressure on the CAD flow. FPGA routers do have pretty good hold time of violation resolution code, and it makes them more complicated. Commercial FPGA routers are more complicated than most of the papers you'll read on FPGA routing because they have to deal with hold times as well. Yeah, well, you do get reg-to-reg connections, so it's a valid concern. It is a real trade-off. It's just so the hold time problem. Hold time is a real downside of pulse latches. It's just FPGAs can tolerate it better than most things. But I'm definitely not saying it's not an issue at all. It does make the FPGA router work harder if you get a lot of these hold violations, and it does chew up more routing, which gets to be a problem if it becomes excessive. Okay, if there are no more questions, then I'm going to sign off. So if anyone else has another question, go ahead and ask. Okay. Thanks, everyone. Good night. And I managed to not record part of the lesson, so sorry about that. So got to remember after I pause recording to always restart it.
It still shows that you're recording.
I hit it again after a while, but I missed it for a while. So I have to, oh well.